Okay, so my research field is in synthetic organic chemistry. And this is a subject that combines creativity and science. And we can call it the architecture or maybe the Lego of science. As this young searcher here is maybe taking imagination from nature, trying to create something where the only limitation is her creativity. The same stands for this researcher here, but it's in another scale. Let's say that this young searcher here has seen a cat or a kitten. She wants to build one with Lego. And she maybe makes this kitten, but maybe it doesn't fit in her game. Maybe she puts wings on the kitten. Maybe she puts a horn on the kitten just to fit into the game better. The same thing stands for the researcher. She also takes inspiration from the nature. This is a molecule that you find in a plant, and it's a very big molecule. It's actually the biggest molecule that has been synthesized. And maybe she finds that this part is enough. It's a perfect anti-tumor drug. Or this part here is a perfect Alzheimer drug. Here, the creativity, the inspiration from nature, and of course, understanding on biological systems is the limitations. So these molecules are not only important for pharmaceuticals. You'll find them all around you. For example, a pair of jeans will contain about 100 organic substances. You find them in, perfumes, aftershaves, or cocktails of organic compounds. I mentioned medicines, and Lars Balzer will continue after me to talk about the importance of medicines. This is a tasty example. There's a lot of organic compounds in food. And a new and emerging field is molecular electronics. And in your current phones, the electrons are transported through metal wires. In the future, or already present, you can have organic molecules that transport these electrons with completely new applications. So a question to ask is, how do we prepare these molecules? And what do we start with? What is our Lego pieces in organic chemistry? And a way to answer this is to look at the Nobel Prizes, the last Nobel Prizes from this century in synthetic organic chemistry. And the first one is asymmetric hydrogenation of double bonds here. Another one is olefin metathesis, where these substituents change places. And a third one, from the latest one from 2010, is the cross-coupling reaction. And you see there's two things in common for all these reactions. First of all you make use of a transition metal catalyst. It's a catalyst that makes the transformation possible. And secondly, is that all of them use these alkenes, these double bonds, olefins. So where do we get these olefins? Do they grow on trees? No. We take them up by fracking, by drilling, or we dig out tar sands and coal. And for a Nordic country like Sweden, I think it would be worthwhile to use a renewable carbon source for our medicines, our materials, and our clothing. And if we go to the biomass, we can roughly divide it into two parts. We have the eatable biomass, and we have the non-eatable biomass. And if we should choose one for organic synthesis, I think we should vote for this one and eat this one instead. If we look into the non-foodie biomass, this is actually the raw material for Sweden's biggest industry, namely the paper and pulp industry. And in the paper and pulp industry, you extract cellulose, this molecule, from the wood. And you make paper out of it, but you also make viscose, clothing out of it. You also get out something that's called hemicellulose, and you can ferment this to ethanol. So these two products are high-value products in the paper mill. Then you also get out something that's called lignin. And lignin is considered a low-value product. And this low-value product is heated or burnt to generate process heat, and also you can couple a turbine to it to make electricity. So if you look at all these molecules, you see the OHs, you see the hydroxyl groups, you see the alcohols. You have primary, secondary, you have benzylic, you have phenolic alcohols. But you don't see any alkenes, right? You don't see any double bonds here. So then the question is, how many Nobel Prizes do we have in transforming these alcohols? 0. How well do we perform when we try to do it? Not very well. If we want to transform this alcohol to this product here, we cannot do it. We have to go through an intermediate. And going through this intermediate will cost us a lot of chemicals. Both, we need chemicals to prepare this intermediate, but also this intermediate will lead to a very big amount of waste. So if you make 1 kilogram of this compound, you will generate 10 kilograms of chemical waste. And this is, of course, not sustainable, right? So here, my friends, here is where you, your children, and probably your grandchildren will contribute in organic chemistry in the future, because we need to solve this. I will show you very quickly how my research group worked on this. And we have taken wood as a raw material. And in the wood, we have the lignin. So we aim for the lignin, the low-value source. And in lignin, 50% of the chemical bond is this bond. So we target this bond. And then we perform a pulping in ethanol and water. And we add one of these metals, a catalyst. And we get 51% yield of this monomer here. And taking into account that it's only 50%, it's actually a very, very high yield. But besides getting this interesting compound, we also get paper pulp out of this. We get hemicelluloses, we can make ethanol, and we get also a bio-oil that we can use for certain applications. But if we go back to this molecule, you can see that this is actually a pretty good Lego piece for organic chemists. We can make vanillin out of it. We can make something that smells good, maybe tastes good too. Starting blocks for pharmaceuticals, and also we can make polymers out of them. Finally, I just want to show you how we not only work on a small scale. So this is not at Uppsala University. This is off-site. And we're transforming not wood. We have taken lignin out from a paper and pulp industry. And we're transforming it into something that is evaluated for a biofuel at the moment. But it's just the lignin part here. But I want to emphasize that the recipe has been researched here in Uppsala. Okay, thank you.